Okay, so I handed out a copy of previous year's test two. Why do you think I did that? Because of what happens next Monday. Test two. So our second test, which I cleverly call test two, because it follows test one. Kind of clever that way, isn't it? Test two is next Monday. Okay. What does it cover? It's going to start with special relativity and go up through circular motion. Okay. So it starts with special relativity. Okay. It goes up to circular motion. Okay, it's the same format as before because I only know how to give three types of tests. One for a class like this, one for non-science majors, and one for our program classes. That's I don't know how to give three tests. So look over the stuff on Monday. What we'll do, the same format as before. On Monday, next Monday, I'll start off the class if there's any questions, and I'll continue to answer questions until the questions stop. Then we'll go on with new material. Okay, but I do promise one thing on there. What do I promise? I promise there will be a separations of variable question. So if you look at this exam here, it was question, in this case here was question 6. So there will be a separation of variables differential equation. And guess what? You're going to see it again next semester. So that's part of the reason why I'm putting it in here. One, it's a very standard technique you have to be able to do. And also, I want to get you prepared for the second semester, which if rightly or wrongly, I'll be teaching. Sorry, guys, or good, depending on how you look at it. We're going to see it also there as well. We're going to see it actually quite a bit next semester. And so we have to get ready for it. Questions? Okay, so all I want to do today is just circular motion problems. So let's do a classic question here. I have a string here like this. Here's a mass. Let's say this string has a length of 2 meters. Let's say this mass here is going to be 1 kilogram. Okay. And this is going to spin in a circle like this. So it spins in a horizontal circle like that. So it'd be something where it'd be like this. Okay. If you want the fancy name for this, this is called a conical pendulum. And what we're going to do is we're going to do a couple things in here. Okay. Part A, we're going to find the tension and the string. For part B, we're going to find the speed of the mass. For part C, we're going to find the period of the mass. And what does the period of this object mean? Yeah, the period is going to be the time it takes to go around once. And what we're going to do pretty soon, we're going to look at gravitation. We'll probably start that today. We're going to figure out how long it takes actually for the Earth to go around the sun. That turns out to be 1 year. Imagine that. How many days is it? 365, and we'll see why it's 365 days. When you work it out, that's what you get. Okay, so start the problem. Perfectly fair question on test 2. So if you look at that, what would you do? Why would you do a free body diagram? Yeah, you're hearing tension, you're hearing force words, think free body diagram. What's the brain dead reason? It's not going to hurt. So if you have no clue what to do, you draw a free body diagram. And so again, I'm going to tell you again, when I pick up this test, I can usually tell whether somebody's doing well or not, because I look at a question, and what don't I see? A free body diagram. If there's not a free body diagram, with the exception of the relativity question, probably that problem's going really bad. Okay, you need that free body diagram. Okay, so let's start off with this. There. What are all the forces acting on my little friend there? Going? Yeah, always along the direction of the string. And going straight down. Now, okay, so you always start off with a free body diagram. What is the coordinate system for any circular motion problem? And also, why do we know it's a circular motion problem? It's going in a circle. Okay, if you see the thing going in a circle, it's a circular motion problem. So what is our coordinate system for any circular motion problem? Radial and then perpendicular. Now, what is the radial direction in this case here? Why isn't it like this? It's not. But why couldn't you say, oh, it's going to be something like this? Okay, where's the circle? The circle's like this. It's a horizontal circle. When we talk about the radial direction, it's radial to that circle we're moving in. So since this is a horizontal circle, the radial direction is going to be like this. This will be radial, and this will be perpendicular. And which way do we always take to be positive in the radial motion? Toward the center of the circle. Okay, so this right here is going to be positive. Now, what about the perpendicular direction? Which way is it moving? So this is just going like this. It's not. So which way is positive? Doesn't matter. We can take up to be positive, we can take down to be positive, it doesn't matter. Does that make sense? Okay. So I'll take up to be positive for no good reason. Okay. You proceed to tell me what, and we need a angle here. Imagine that the angle's 30 degrees. Okay. Crazy. Proceed. Yep. That sounds great. Which one gets broken up?
That one. Or that.
Do I break up this guy or do I break up this guy? The T, how come? Yeah, this MG is in our perpendicular direction. That doesn't have to be broken up. This T, though, is actually in both, so we have to break that one up. So what can we do? I can break this up like this. For perpendicular components, this I'm going to call T rad for T radial. This I'll call T perpendicular for the perpendicular up there. Okay. What do I write next? F net equals MA. Hey, what next? Okay, say it right. Your thinking is completely right, but just radial and perpendicular. So I'm going to say this is F net radial. Was MA radial? And then F net perpendicular. MA perpendicular. Okay, sadly, I'll put it over here because I need the picture still. Okay. What do we get for the perpendicular direction?
T perpendicular.
Okay, that's right. So if you look at T perpendicular here, I'm taking up to be positive for no good reason. So it's going to be T perpendicular minus the MG here. equals. What is my acceleration in the perpendicular direction? It's 0 because it's not moving. Now, if you want to figure out how to do motion like this, let's say that this was going, it just wasn't going in a circle. Let's say it was oscillating like this around a circle. You can work that out, but out with what we have here. If you want to see how that works out, take our course in classical mechanics. I'll show you how to do that. It's an absolutely gorgeous calculation that involves something referred to as a Lagrangian, which is actually one of these, when you're in physics and you start writing things in Lagrangians, you've taken a huge step in your education. It's this absolutely elegant formulation of classical mechanics, which goes over perfectly to quantum mechanics and everything else. But I digress. Okay, so now tell me what to do with this. What is my friend? So this tells me T perpendicular is mg. So tell me about my friend T perpendicular from the picture there. Okay, here's theta. So what is my friend T perpendicular? T cosine of theta equals mg. So my T is nothing but mg over cosine of theta. So I can put in my numbers. I have this, what was my mass? 1?
Yes.
1 times 9.8 times the cosine of 30 degrees. Okay, and that'd be my tension. What is cosine of 30 degrees again? That's sine. It's a 0.866. It's the square root of 3 over 2. Okay. So if you wanted to, you can write this as 1 times 9.8 square root of 3, then times 2. In other words, 2 times 9.8 over the square root of 3. Okay. Questions for that? Okay. Part A is done. Part B was figuring out the speed of the thing going around. Okay, so how do we do that? What?
So, T, UD2.
We do the radial part. Okay. So in that pit, we need some space for this. Yeah, that's really not enough room, is it? Put it up here. Okay, that's not radial. Okay, what is, from my free body diagram, what is your net force in the radial direction? Just as T rad, okay? Mg is a perpendicular, and then the T perpendicular is a perpendicular force, so I only have the T rad. It's MA radial. So from that picture, what is my radial acceleration? I mean, my radial tension? T sine theta. What do you know about A radial? A radial is? What is radial acceleration always? The circular motion? What is it always?
V squared over.
V squared over R. What is R? R is the of the circle. So this is radius here. What would that radius be in this case? So I put in a 2. I agree now. Yeah, you go here. Here's your radius. This is 30 degrees. This is L. So my R is, I call this the length of the string. That would be L, sine of 30. This would be 2 sine of 30. Okay, now what is sine of 30? A half. So this is going to be 1. Okay. Now, do I know anything special about my T? I know it's this number here, but I want to be a little more fancy with that. Do I know anything else about T? What else do we know about this T here? Do we know anything general about that tension? We got the value, but what about general? The tension is also mg over cosine theta. So I can take this, and I can put that up into here. If I do that. What does that give me? That gives me mg over cosine of theta times sine of theta, right? Here's my friend t. Yeah, p sine theta equals mv squared over r. Now this is why you don't put in numbers until the end. Does anything special happen there? I agree. What happens? Two things. The sine over cosine is my buddy, the tangent, and the masses cancel. So if I were to replace that 2 kilogram, that 1 kilogram mass with an elephant, somehow I could swing this thing. What would happen here? Would there be any change? It's independent of the mass, right? The masses here are canceling. So this is giving me g tangent of theta, because of the sine over the cosine, equals v squared over r. I take over the r, take the square root, and so this gives me that v is rg tangent of theta, square root thereof. Pretty slick. We put in the numbers, what do we get? We get 1 times 9.8 tangent of 30 degrees. That'd be my speed of that object going around. Does that make sense? Questions? You look like you have a question, Harvey.
Yeah, I just don't know what it is.
Okay, that's fine. When you think about it, just ask away.
Why can't we just use the value we found for T? Why?
You could go through and do that. The reason why you wouldn't is because what you see about this is that the speed doesn't depend on the mass. And if you put in this value here like that, you'd be losing that information. You get the right answer. It's not wrong. Okay. But you'd be losing some information, like the information of the speed here doesn't depend on the mass. So you never put in numbers until the very end, because often you can get little things occurring like that. That takes a while to get used to that. Questions? I think there's a part B to this, frequently called part C. Part C was in how long does it take for this thing to go around once? Any questions on this part? So how long does it take M travel once around the circle? In other words, i.e. find the period. What do we do with that? Hey, what's the distance around a circle? The circumference, which is 2 pi r. Keep going. Doing great. What do we know about that speed as it goes around that circle? It's a constant. So the speed is the constant around that circle. So the fact that the speed is a constant around the circle, what can I do? I can take the distance it takes to go around and divide that by the period, the time it takes to go around once. And that would have to then equal the speed. Okay, so since the magnitude of v is a constant, I can say that this magnitude of v is going to be the distance over the time. So this V here, which we have, is going to be this 2 pi r over the period P. Okay, just so you know, period is almost universally called T, capital T. I'm not using capital T because we have a tension here. But almost always in anything, capital T is your period, unless it's the temperature. Okay.
For tests, is that what?
I don't, as long as it's clear to me what you're doing, I don't care. Okay. I just want you to be familiar with the standard notation. So that if you pick up some book and you see this random T, you realize it's probably going to be the period if it's in classical mechanics. If it's thermodynamics, then it's going to be the temperature. Take a course in general relativity, it's going to be basically the energy density. It's going to be your energy momentum tensor. That's the different place. Okay. So we have our friend V. We have our friend P. I can now solve for T. So if I put that in here, I'm going to take my friend V, put it in here. I'm going to say my friend V is the square root of RG, tangent of theta. And that's going to equal my friend 2 pi r, or the period. Take the T over here, my square root stuff over here. And tell me why I probably won't leave it like that. Because I'm wrong. Tell me about R. You're right. I have an R here and an R down here. What would you do? You'd write them as one overall R term. And so what would be the overall R term? If I have R over the square root of R, what's that going to be? R is the 1/2. So just saying it would really be the period. Again, this isn't wrong, but the way you want to start writing things, you want to start writing them as you're going to see them in textbooks and papers. They'd be like that. Then you put in your numbers in Shazam, you would have yourself the time it takes for that to go around once. Pretty simple.
We just left it like that.
So no, if you left it like what?
First,
If you left it like this, I might do my generic like that, but I would not take off anything. But you would still have to endure my grr, feel intimidated by it. Questions? Let's try another one. Okay. This is the top view. Okay, so here's a road. There's a road, and here's a car. The car is traveling this way. There's some velocity here. Okay. And there's some radius here. There's some radius here of that road. Okay. And what I want to do is I want to figure out the maximum speed that this car can have before it slides off the road. So this is going to be a flat road. So this is a flat road. Let's ask what is the maximum speed of the car before it slides off the road. Also, I'm going to explain bad driving here. Okay, well, something that I'm guilty of myself. But there's something people do instinctively. I want to explain the instinct that you do. Okay, so we have here's a road. Car is whooping around here like this. I want to figure out the maximum speed that this car can have before it can't go around the road. It just goes off into the cornfield. What?
So there must be a new one.
The number of cars I see in cornfields that I drive here are actually larger than you would think. Okay. In fact, actually, the last weekend, actually, at around midnight when we had the windstorm, we thought it was a problem with the windstorm, but it wasn't. It turns out that somebody went down this one hill that's not too far from where my wife and I live. Lost control, went through the only flashing light in the town, which this is in Branchport. Fortunately, no one was there. Went to go turn. Somebody tipped over on the side, skidded, and took out two gas pumps in this one garage. It didn't start a fire. I don't know how. Then smashed into a telephone pole and took up a telephone pole. So, things like this happen. Somehow they survived. And the gas stations did not, the gas pumps did not explode out of it. Okay. Solve it. Yes, it's a free body diagram. Now this one's going to be a little on the tricky side because I'm going to draw two different diagrams. I'm going to draw a top view, then a side view. So let's draw the top view. And then a side view. In other words, what you'd see from the road. So this is going to be the top view one. So this is here. Okay. If I'm looking at a side view, what am I going to do? I'm going to have the car here and here are the tires. So I'm kind of looking at the back end of the car. So let's do this one here. So if I'm looking actually, if I'm standing here, if I'm looking at the back end of the car, what would be all the forces on this right here? Okay, let's start with the easy one, then we're going to go with what you said, and you said it correctly. Go with the obvious ones. The MG going down, and then the normal. Okay, if I had to put those over here, where would they be? You know, the normal would be coming out. Remember how I said you denote something coming out of the board? I think I mentioned this once. You put a dot with a circle on it. So if I put a dot with a circle on it, this means a dot with a circle means out of the board. That would be the normal. And then how do then the weight is in doing what in this picture? Into the board. And so X with a circle means this means into the board. And that would be your weight. Okay, so they're the more obvious ones. Now, if you have something going a circle, there is no magic circle force. There are always real forces that give rise to circular motion. What would actually be the force that causes a circle? And you mentioned it before, Willie. It's going to be friction. Now, there's going to be friction going on the tires this way. Okay, there's like this. I'll just call it generically. There's going to be friction. In this case here, there's going to be friction like this. Now, here's the important thing. What kind of friction is that? We have kinetic, and we also have static. Now, it's not obvious which one this is. Okay. I'm going to state something which is going to sound very stupid. I'll prove it later on. I'm not going to prove it today. It turns out it's going to be static friction. This is going to be static friction. You could say, well, how? The car is moving. It has to be kinetic friction. What I'll prove later on is that if I have a tire, if the tire is rotating this way, if you look at the point of contact where that tire is, if that tire isn't sliding, that point of contact has no velocity. If it has no velocity, then it actually is static friction. So I'm just going to write this as a fact, and I'll prove it later on.
Can you explain that more?
I can, but I didn't bring a tire with me. Hang on. Okay, let me get a tire out. Okay, so let me kind of illustrate this out. Try to illustrate this. Well, this is something that's not going to come out on the screen. I can, and the recording can't deal with that or help that. So this tire here, if it's rolling like this, and it's not sliding, this is sliding. All right, this is when you're sliding. This is rolling without sliding. This point of contact has no velocity. So let me write that down, then I'll try to convince you of that. So when a tire rolls without sliding, the point of contact of the tire with the road has no velocity, which sounds utterly stupid. And let me try to convince you why this is the case. So let's say here's a tire, and it's going to go this way, and it's going to roll without sliding. The claim is that this point of contact here has no velocity. Okay, so if it has no velocity, then the friction on here then has to be static friction, of course. That's why that's going to come in. So let me try to convince you of this. So first of all, if this tire is going like this, okay, which way is it rotating? It's rotating this way. That's how the tire is rotating. Okay? Now I can view this motion as being two things. Okay, let me, before I say this, you actually know this point. Okay, imagine I clap my hands and I make you 7, and you're on your bike. You're on your little two-wheeler or three, it don't matter what it is. You're on your bike and you're riding on the sidewalks or on the road after a rainstorm. What does every 7-year-old kid know? And every 7-year-old kid does this. So you're on your bike after a rainstorm. You're riding your bike and you look down at the sidewalk or the road and you see something. What do you see?
Oh,
Mark? There's water. Well, what do you notice in the water? For instance, if this is your tire, when you're on your bike and you look down, see the water on the road, but what else do you see? You see the tread of your tire actually in the water. It doesn't last long because the water comes back in here. If this tire were just going like this, if it were sliding, it would completely wipe out that tread. You wouldn't see it. So the very fact that you can look down during a rainstorm when you're a kid, and you see actually the imprint of the tire tread in the water here momentarily, that indicates that this point of contact has no velocity. So every kid knows this. You just don't think about it when you're a kid because you're riding with your friends and having fun. Okay, so this motion here, I can think of it as being two motions here. So this right here, this motion here, I'm going to say it's two motions. It's going to be a pure translation and a pure rotation. Okay, so pure translation, what do you think? If this is a pure translation, what do you think that means? This is a translation. The whole thing as a unit just moves like this. So this would be here is that if I were to look at if I were to look at 3 points here, A, B, and C. These all move with the same velocity of V. Pure rotation, if I look at these same points here, A, B, and C. If this is a pure rotation, rotating this way here, what's the velocity of A? What direction? This way. What's the velocity of the center? 0. The velocity of C? This way. If I add these two things together, what do I get? Point of contact here has no velocity. They cancel. The center, B, has a velocity here, v. And what about the rim? Gonna be 2v. Okay. This is rolling without slipping. Well, the reason why that's important is that this is going to be static frictional force. And you tell me how to then do the problem. What kind of problem is this? Car is going around the road. This is a circular motion problem. How do you know it's a circular motion problem? It's going in a circle. So let's go through and do this one here. So if I were to draw my coordinates listed over here, if I were to draw my coordinate here, what would I have? I'd have my perpendicular, then I have my radial. Which way would be positive here? Toward the center of the circle, right? Because here's my road. My car is here. This right here is the radial direction. This is my positive direction. Okay, how do I proceed? F naught equals MA. Yeah, break it into a perpendicular part. I mean, sorry, a radial part. Perpendicular. Okay, what do I get from a radial part? In this free body diagram, what is my only radial force? Your static frictional force. What do you know about the A radial? It's always V squared over R. Okay, now let's go over here. What is your perpendicular acceleration up and down? What's your acceleration in the up and down direction? Zero. So what does it mean about the normal and then the weight? They have to be equal. So there is no perpendicular acceleration, so this means that m equals mg. Okay, so let's go through and do this. So I have my static frictional force has to equal this. Oh, do we know anything special about static equilibrium, about static frictional forces? Yes. What do we know? They are less than or equal to mu sub s. What is mu sub s? Okay, there is an n. Okay. Mu sub s is the coefficient of static friction. You have that here. Your n is what? It's mg here. So if I put this all together, I get mv squared r less than or equal to mu sub s mg. What nice thing happens? The m's cancel. And take over my r. So what is my v maximum speed? Has to be the equality. That's how fast this can be. You can go. So what happens if you exceed that value? And the static frictional force gives you enough force to basically make the corner? No. So then your friction becomes kinetic. And what does your little car do? It goes right off the road. Okay. And this is actually how you can determine actually the speed of these on the roads. If you know the mu sub s, and that's going to vary, but you'd have some estimate of that. You know the radius of the road, you know you're on Earth. That actually tells you your maximum speed, and then any good engineer is not going to set it for the maximum speed, they're going to lower it some. But that's actually how you determine these values. Yes, Riley?
I don't know if I just missed this, but what's the coordinate?
It's always going to be radial and then perpendicular.
Yeah, would it be the direction that the car is going?
No, so the radial is always radius of the circle. Okay, so if your country road's like this, okay, if your car is here, this is a radio. I always make my radio like that, and then I take this to the positive. It's over here, and it's like this. Okay.
So for the top view, would it be like?
So in the top view here, when we had this guy here, we had our static frictional force here, and our normal, and our mg. What's our radio direction here? Yeah, here's perpendicular. Here's radial, and so this right here is repulsive. Okay. Make sense? Now, okay, let's say you have a flat road here, and let's say you're late for work, perhaps. This sometimes happens. And it's a flat, so you can, maybe it's in the morning, and you can see that no other cars are coming your way. And you have a curve, and you don't want to slow up because you're late for work. What do? And you just do this instinctively without thinking about it. So let's draw this out. So here's some country road. You're going this way. And you don't want to slow up because you're late for work. What do?
So there's no one.
There's no other clues.
You just go straight through.
Do something more.
You cross the line, you just go straight.
You take your car and you go into this lane here, like that. Why do you go into the other lane? You'll do this instinctively. You're not going to do some little mental calculation. I'm going in a circular motion. Reserve for my note. You just do this instinctively. Why? Because you don't want to slow up. So let's say you're going at a speed greater than this value here. Why do you then instinctively move into the other lane? The R actually gets bigger. What's going to happen here is that there's going to be some R for this. Okay. When you actually go into the other lane like that, what you're actually doing is effectively making a larger R. If you're making a larger R, your Vmax is going to be larger. That allows you to get around the road. That's kind of cool. You don't think about it that way. That's actually what happens. That makes sense? Questions?
If we were to like have a question about this,
So,
can we use that same equation that we found and just?
you can, as long as you use it correctly. The problem with just using an equation and not going through the work is, let's say you do that. And let's say you didn't realize that there's a subtlety in the question and you have no work done other than that thing there. The only thing I can do is just take off everything because there's no work. There's just random equation with no work. And so I can't say, oh, Raleigh just made a mistake on X, oh, -1. Because if I see no work and then just this random equation coming out of nowhere and it's wrong, all I can do is, with my cats, because my cats grade the exam, they'll just, take that off and then go and chase chipmunks, which is what they do. So you'd always try to show your work. And not only that, it's going over it again will actually help you. And you're going to have a homework question where you have to deal with this.
How long we just got?
The one that's actually in the brand new shiny homework 6. Everyone have homework 6? You do not? You have? Okay.
Which question is it?
I don't know. I can't wait to find out. Okay. Questions with this? Okay. So let's say you want to design a road, right? This actually depends on what? It depends on static friction. And that's fine, but what happens? It rains. And if it rains, what happens to your mu sub s? It goes down. Suppose you wanted to design a road that doesn't have to rely on friction. What do you then do?
Like a frictionless road?
Well, I don't, in other words, for me to go around a circle here, going around a circle here depends on the coefficient, depends on static friction. I don't want that. I want a road that's independent of that static friction and make it easier for, I don't have to even worry about the weather as much. What? Something more basic. Often when you go around a curve, what do you notice about the road? It's banked. Okay, so what I want to show you is why you bank a circular road often. There's a reason why you do it. So it's going to get rid of basically your static frictional force or the necessity. So how can we design a road? Let's say a circular road that doesn't have to rely on static frictional force. Right? The answer is we're going to bank it. We bank the road. Okay, so we'll finish this up on tomorrow, but let's start the picture. So if I bank a road, what does it mean? It means it's at an angle. So here's a road like this. And I can draw the back end of the car. So here's our car. Here are the tires like this. Which way is the velocity here? Is going around like this? If you're into the board, how would I denote a velocity going into the board? I put an X here like this, and I put a V here like that. So that's the velocity into the. So car is traveling into. Hey, what's the next step? We write a diagram. What are all the forces acting in my car? And let's assume the road is frictionless. And that's it. So I have my normal force. And here's my mg. Now set up this next part, and then we'll finish it up tomorrow. Now, here's the tricky part. What is my coordinate system? There's a really tempting wrong coordinate system. What do you think the tempting wrong coordinate system is? Skewed. Think, oh, I've seen this, inclined plane. I'm going to do my regular coordinate system like this. Right? I'll make this radial, I'll make this perpendicular, vice versa. It doesn't really matter. Okay, tell me why that is entirely wrong. Where is your circle here? Yeah, this right here, that is my radius here, right? The car is going around like this, right? So this is my radius. So how's my radial coordinate have to go? My coordinate system has to be perpendicular, and then this is our radial, and toward the center of the circle is positive. Okay, so what we'll do, we'll set up this problem here tomorrow, and what we're going to find out is that the normal force here is going to supply actually your forcing around a circle. It won't be friction anymore. And so you don't have to worry about whether it rains or not. Well, you have to worry about it for other reasons, but or snow. Okay, have a great day. I'll see you in lab this afternoon. We have a circular motion lab. Yes.